There we go. So this material I presented at a conference in 2015, and there was a paper that's published, and there's the URL if you want to look for some more details, but we'll give you some of the highlights. We can see from history that science has limitations. So from the history of science, we can see this. We can see what science can say and what it cannot say. And we'll look at the reactions, what happens, what do people do when the data seem to conflict with our favorite theory. And we'll look at how this contrasts with the biblical worldview. So science is often thought of as proving universal truths. Science proves things. And even when it's not stated clearly, this is an underlying assumption which people have. But that is not actually part of science itself. It is the fundamental postulate of what philosophers call scientism. That is a belief beyond science, a belief that science is the only path to knowledge. And scientists themselves shouldn't say that. That is not a statement of science. That is a faith. We believe so much in science. Well, science is useful, but this is more than we can claim. So I would say that is not a valid, that is not a warranted view. And we can show that looking at some examples. So we'll go back to the ancient times. We'll look at how planets were discovered and how the motion was understood. Now, today we have so many things. We have many activities, and we don't have to go to bed the moment the sun goes down, so there are lots of other things we can do. But in ancient times, people noticed the stars. So the motion of the stars was uppermost in people's minds. It was considered significant. And trying to understand this, people tried to make explanations, figure it out. And these tentative explanations are part of the saga of discovery. And actually, we'll see how theories are constructed. So the theory seems to work, and then we check it against the data. We look at the stars, we look at the planets, and we see, do these fit with our explanation? And what will happen? Reactions that can happen. We can maybe deny the observations. We say, you made a mistake. I believe my theory. Or maybe we deny the theory. We say, well, that's only a theory. You don't really know. I saw what I saw. I know what I saw. So we could disagree with one or the other, or we might have to modify our theory, find a better theory, replace or modify. And this, we can see this right from the time of the ancient Greeks. So let's start with Aristotle, who said the explanation for the movement of the planets and the stars and the sun, the moon, is earthly matter stays on earth and heavenly matter stays in the sky, stays in the heavens. So the circle is the most perfect of all figures. So things in the heaven are perfect and they'll circle around. So that's why they're circling. And things on earth fall down to the earth. So this was his explanation, a summary, and that's called the geocentric view. Geo is the earth and centric, so centered on the earth, geocentric. And today we'd say this is kind of simplistic, but what happens if you drop a rock? It's going to fall to the ground. This is clearly earthly matter. It seems to work. If I drop a ball, it falls to the ground. But the moon is up there circling around us. So it sort of seems to fit, even though today, obviously, we say this is a very simple worldview. But this fits with our experience, at least to a certain extent. So there were some problems with this view. One is not all stars just seem to cross the sky. If you have ever looked up at the stars, you know from hour to hour they're moving, crossing the sky. But we have some unexplained things going on. They're called the wanderers. Now, in Greek, the word for wanderer was planetes. So planets are the wanderers. These are the stars that don't just seem to follow the other patterns. And so this is a problem. Sometimes the planet moves faster than the other stars, and sometimes it backs up, goes backwards. It's called retrograde motion. And Aristotle's explanation didn't work for this. So people began modifying this, trying to figure out a way. Here's one way. Ptolemy, in the first 100 or so years after Christ, had this idea of epicycles. An epicycle is a cycle on a cycle. So if any of you someday decide to be theologians, you'll have to take Greek. And epi means on top of. It's a Greek prefix that we use in a lot of different cases. And here it means a cycle on top of a cycle. So imagine that small circle going around on the bigger circle. In fact, you won't have to imagine. Here's an animation of it. So look at the red circle. It's on an epicycle, but that epicycle is also going around the big circle. And that makes a complicated pattern. In the picture to the bottom right, you'll see our point of view. We seem to see that red planet, this is to represent Mars, right? Seems to sometimes go forward across the sky faster than the other planets and sometimes back up. Wow, we've got an explanation. That's pretty cool. And so we could track Mars as it goes moving through the other constellations, sometimes backing up, but usually going faster. Nice. We've got a model. This was accepted for over 1,000 years, 1,400 years, and it let people make predictions. Wow, this is what science is supposed to do. Let you explain what you see and predict where will Mars be tomorrow night? Where will it be next year? Okay, we'll say, oh, it's going to be in this part of the sky. And that's the power of science. That's an extremely successful scientific theory, if it lets you predict stuff. But today, we say it was wrong. It was incorrect. Now, that should make us think. It worked for so long, and yet it's wrong. So it was replaced by a better theory, and let's look at that. But the take-home story here is theories are tentative. They're not proven. Even if it works, it's not proven. Now, we're going to use it as long as it works. So science is very, very useful, but science is tentative. So science is valuable, but let's put it in perspective. It's important to understand its limitations. If I'm going to use a power drill or some tool, I'd like to know how to use it well and do the job and not hurt myself. So science is the most powerful thing that humans have ever made. It helps us understand the world and then do powerful things and build our civilization. It is careful thinking. That's what it is. Careful, logical thinking to explore the universe and explain these mysteries. But it isn't a proof. Okay, so here we see a reaction to conflict. The original geocentric model, heavenly matter, earthly matter, didn't quite work. So we fix it, the retrograde motion of the planets, we fix it by adding these epicycles. So heavenly matter goes in circles, but it's circles on circles. See that little tweak? So that adds better explanation power. But it's an extra complication. It has two problems. They are, these epicycles are very arbitrary. By the way, the big circle is called the deferent, the small circle is the epicycle, and it's pretty arbitrary. And the size of the epicycles was arbitrary. And the fact is, if you make enough arbitrary changes, you could make that cycle be anything you wanted. My father-in-law used to say, that paper would lie still for you to write anything on it, for you to print anything on it. If it's too open-ended, then we can't really trust it. And this is the problem with epicycles. So here are some different patterns that you can fit with different epicycles. I hope you see that doesn't look very natural. And in fact, it can fit anything. That's not what science is supposed to do. It's supposed to explain what actually is and make sense. It's not supposed to fit just anything under the sun. In fact, if you have if you have many cycles on top of cycles, you can do strange things like this YouTube clip. This is, I don't know, maybe 100 epicycles, and you can fit just about anything you like. So we're having that and that imaginary planet, we're drawing out its path. Tell me when you recognize this path. Yeah, that is a very complicated orbit. I don't think this is anything natural, folks. This does not teach us anything fundamental about how nature works. All right. Yep. If you have enough epicycles, you can do anything, and it's basically meaningless. Nothing fundamental learned here. You can choose any numbers to fit. I can roll some dice, and then I'll just fit a function to those numbers. So I have some dots, and I just put enough squiggles, I can fit anything. There's no pattern yet. So this is not how science should work. Yet, the epicycle explanation was treated as truth for 1,400 years. And I'd call it dogma. It was just, this you must believe. It's like your faith. Otherwise, will excommunicate you, maybe. So this is also not how science should be. We should test our explanations, not just say, well, this is what was taught. But yeah, let's look at it. Let's do some experiments. So we come up to the time of Copernicus. Nicholas Copernicus is the one who said, oh, the Earth is not the center. The sun is the center. This is called the heliocentric model. Helios is the Greek word for sun. So Copernicus puts the sun at the center. He did this in his book in 1453 on the revolutions of the heavenly spheres. So he's explaining the motion in the heavens, in the skies, but he says the sun is in the middle. He doesn't need epicycles anymore. So this is a simpler explanation. That's good. The sun is at the center, and the planets, Mars, Venus, but also the Earth is orbiting, circling around the sun. Let's see what this does for us. So again, we have a little animation to show. I've got two planets. We'll have the red one is still Mars, and the blue one, that'll be the Earth, right? The blue planet. So we just see part of the cycle as both Mars and Earth are trying to orbit the sun. And since we're on a moving platform now, and we sometimes see Mars going fast, well, Mars is going around, yes, so we see Mars moving. But sometimes Earth comes around and is passing Mars. I think probably you've had the experience of sitting in a car at a stoplight, and suddenly you wonder if is my car rolling? Because I had this, well, I caught out of the corner of my eye the car next to me was moving. So we're not sure who's doing the moving. And just for a moment, we have to ask, are we rolling? Oh no, it's they're moving. So this is the view looking at Mars when we ourselves are moving. So Mars may seem to back up, that's the retrograde motion, but it's really the Earth that's moving forward. So it's simple circles, and yet it explains why sometimes Mars seems to go forward across the sky, and sometimes it seems to back up. That's when Earth is overtaking it, catching up. So what have we got now? A simpler explanation, and yet it turned out with these simpler paths, no epicycles, just plain circles, we get extra power to explain other things, like the day, the seasons, the year. These are all the rotation, the Earth spinning on its axis, and the Earth going around the sun. Kid stuff. You all know this. But it was simpler than the old model. And so we see an example of replacing an old model by a new model. That's called a paradigm shift. When you have a new theory and you say, I was wrong. We've got a better explanation. Now, this explanation was simpler to understand. No more complicated, funny orbits, but simple circles. It was more elegant. You'll hear that word in science and in mathematics, an elegant explanation. That may mean it as a simple math formula rather than some complicated thing, or it may have some structure that the scientists say is beautiful in its form. Okay, so this is elegance. But most important, does it let you predict things better? And does it lead to deeper understanding? All these things are, when you change your mind, when you see things from a new light, that's a paradigm shift. That term was popularized by Thomas Kuhn in the famous book, The Structure of Scientific Revolutions. He presents the idea that science doesn't just go gradually, learn more, but it goes in stages. And that a paradigm shift is a revolution in how we understand things differently. Okay, so the question is this new theory truth, or is it just better? Is it more nearly true? Well, remember that science can't prove the theory. We can look for better explanations. We can compare this one to that one. And we can also apply another criterion, which is, does it make sense? Is it consistent in itself? Or does it kind of have a conflict built in? So we look for great internal consistency. We look for simplicity of the explanation. We look for more accurate predictions. And here's the bad news. Copernicus's model with the sun at the center actually didn't do quite as good a job at predictions as the epicycle model. So why did people ever change? I didn't tell you. Maybe this was premature. Maybe they shouldn't have jumped. But Copernicus was a little worried that people wouldn't accept his model, his explanation. We've all heard of Galileo being tried for his scientific theories. Copernicus refused to publish until he was dying. He was on his deathbed. His friend said, hey man, you've just got to tell the world about this. And he finally authorized the book to be published. And he died very shortly the same year, just in a few months. So he didn't have to be tried or burned at the stake or anything. Maybe that was good planning. So no charge of heresy. But speaking of Galileo, Galileo was tried for heresy because he said, this is the way things work. And other people said, oh no, you're disagreeing with the Bible. You're disagreeing with the church. And so he was tried, and he was told, you must recant. You must admit you were wrong. And actually, it seems, in reading the history, that Galileo was a pretty abrasive person. He argued. He didn't say things in a diplomatic way. So probably the trial was more about the enemies he had made rather than the science he was explaining. In fact, Galileo is today probably considered the founder of science in many ways. He explained so many things in motion, and the idea of inertia actually led to relativity, which is a more modern explanation. Galileo did support the sun is at the center, heliocentric view. He discovered all sorts of things using the new invention of the telescope. He was the first one to see the craters on the moon. He was the first one to see sunspots. And this tells me that things in the heavens aren't all perfect. He was the first one to see the phases of Venus. If you look at Venus with the naked eye, you'll see just a very bright star. But Galileo looked through his telescope, and even with binoculars, you can see this. A small telescope, it has different phases like the moon. So it may be a crescent. And when it's a crescent, it's big, and when it's more of a full disk, it's small. And that tells me it's farther away. Okay, so his observation of Venus fits in with the heliocentric model. The sun is the center. Sometimes Venus is on the other side of the sun from us. Sometimes it's on the close side. And then we're seeing mostly the dark part. So that's when we see the crescent. This fit very well. And Galileo also was the first one to see that there are moons orbiting Jupiter. He saw the first 4 largest ones: Io, Europa, Ganymede, and Callisto. Those are called the Galilean moons of Jupiter. So here's another thing. We can now recognize not everything orbits the same thing. Here are some moons that orbit Jupiter, and we have our moon that orbits Earth. And so not everything orbits the Earth. And so this also gives us some reason to believe, yeah, Earth is not the center of everything. So the planets orbit the sun, but then the planets may have their own moons that orbit them. So it all fits. There is a legend that Galileo, while he was recanting and promising to be a good boy and not teach this heresy anymore, he muttered under his breath, "Eppur si muove." I think that's probably Italian. I don't speak Italian. But, and yet it does move. In other words, he says, yes, it does. But I think that is just legend. He recanted, and this story appears for the first time a century after Galileo died. So some hero worshipers told us this story. But it's interesting that the church said, you must change your view of science. And this whole story of Galileo's trial has often been presented as a conflict between science and religion. What do you do when your faith seems to disagree with what your eyes tell you? It's an important question. Okay, so many of these things did fit with the sun is the center, not the earth. Next step, we go to Tycho Brahe, who was a Danish nobleman and amateur astronomer. So he was rich. He could buy as many telescopes as he wanted. He'd go out and look at, actually, no, there were no telescopes. He was too early. He just looked at the stars and put pointers aiming at them and took 25 years worth of data. He couldn't figure out the pattern, too complicated. In his later years, he hired a young assistant, Johannes Kepler, who said, I'm a mathematician, I can explain it, just give me that data and I'll come back in a few days and give you the solution. Well, Tycho gave him the hardest problem, which was the orbit of Mars, and Kepler did come back, but not in a few days. It took him 3 years to find the solution. So here's what Kepler said. We call them Kepler's laws. The first one is the shape of the orbit of the planet is not a circle at all. The planets don't go in circles. They go in ellipses. So the first thing is the shape. Second law is something about how fast the planet goes. It doesn't go at equal speed all the time, but it varies its speed in a way that he was able to describe. And the third law is the period or the time for one complete cycle. So there's a little math in that we won't get into, but you're welcome to take as much math as possible so you understand those things. And I should mention, Galileo said, math is the language God used to create the universe. So to understand it, take a lot of math. But here, Kepler's laws tell us where to find the planets, and they give a better explanation. Just from 3 statements, we're able to predict all these things, and it gives more accurate results. Yay. So is it truth? I hope you know the answer now. Science doesn't prove truth. We can't necessarily depend on the right answer being there yet, but it was better, okay? It's a better model, it fits better, and it says, oh, the Earth isn't the center, but the circle isn't perfect, isn't the idea of perfection anymore either. So he's kind of taking some things away from center stage. Assuming a little, you explain a lot. That's what science should do. That's the hallmark of a good theory. So now let's move to Sir Isaac Newton, probably the greatest scientist of all time, and an amateur theologian. Isaac Newton said of himself, he said that his most important work was writing about God, about theology. He had some very strange views of God, though. So we use his laws of motion today to explain how things move and force and acceleration. He invented calculus in order to derive his theories. So he was a huge mathematician as well as a scientist. This is his simple law. The force between two objects, two masses, depends on the two masses, m1, m2, and it also depends on the distance between them, the radius, r. So it's quite simple. To multiply m1 times m2 and divide by r squared. The g is just a constant of gravitation. So that's really a very simple formula. And one formula, he's able to prove Kepler's laws. So this is simplicity that lets you prove so many things. And it shows a unity in nature because everything attracts everything else. Now, we are small masses, so we don't feel gravity between us and the person sitting next to us. It's too small. But we do feel gravity between us and the Earth. The Earth is a big mass. And there's a gravity between the Earth and the Moon and the Sun and the Earth. And everything attracts everything else. That's a universal principle. And it combines heavenly things and earthly things. This is another sign of good science when you have a bigger explanation. We really now understand something about how things work. Not just the planets orbiting the sun, like Kepler said, but comets, asteroids, everything else will be affected by other things, particularly the sun, which is so huge. It explains why the moon orbits the Earth and why Jupiter's moons orbit Jupiter. It explains why the apple falls to the ground. It explains why there are tides on the Earth and what the shape of the Earth is. It's not a perfect circle, not a perfect sphere. All this is explained by Newton, and that is a huge, wonderful theory. We understand more. We make new predictions, and we see there's a separate change in our worldview, in our philosophy. Not only is the Earth not the center, but it turns out the sun isn't the center either. Because the sun is orbiting in the galaxy. So the sun is orbiting around just like any other star around the center of the galaxy. And different galaxies are orbiting around large masses. So one galaxy pulls on another. So the sun isn't the center either. All objects attract all others. So the reason we thought the sun was the center is it was so big, and it's the largest mass that's close to us. But it orbits too. Now, what is more central now is the idea of universal law. So it's not just a physical, here's the center of the universe, but here's the center of our explanation, of our worldview. So there are ideas that are central, conservation laws, universal gravity, symmetry. These are more central now rather than some physical place. Okay, how does the story of discovery continue? The planet Uranus was discovered accidentally by Sir William Herschel in 1781. And it's a good way to test the theory now. Does it agree with universal gravitation? Does it, and Kepler's laws? Is this new planet in the place where we'd predict it? And does it follow the path we'd predict? Great. This is our first new evidence, our check. And it did give confirmation of the theory. Yay. But it's not proof. In fact, as scientists continued to to plot the position of the new planet through the sky, month after month, year after year, there was a growing discrepancy. So what do? This is a quandary. We don't know what to do. Is Newton's law wrong after all? And then we have some options. We could just ignore the problem. Maybe it'll go away. We could abandon our theory and find a new explanation. That's what Copernicus did. We could adapt the theory a little bit. Kepler did this. Instead of circles, he has ellipses. That's a small adaptation. We could trust the theory and decide there must be some extra factor in the picture that we didn't know about. And there are two guys who said this is the explanation. One was John Couch Adams, who was a university student in England, and the other was Urbain Jean-Joseph Leverrier, a very famous French mathematician and astronomer or physicist. So in 1845, they both said there must be some extra planet out there that's pulling on Uranus to change its path a little bit. There's a new factor. And nobody listened to Adams at all. He was just a student. And in fact, he wrote to some famous scientists and they just kind of ignored him. But Leverrier in Paris wrote to his friend, major astronomer in Germany, and the same week that he got the letter, he started looking through his telescope in the predicted place, and he found Neptune. That was in 1846, September 1846, and it was within just 1 degree of where the prediction said. That was amazing. And in fact, the director of the astronomical observatory called it the noblest triumph of theory. The theory told us where to look, and it was there. A new planet discovered. And that would make us really trust the theory, right? We really now have our reason to trust the theory. So history sort of repeats itself. Here we have a picture of Percival Lowell, American astronomer, who said, you know, when we they tracked the orbit of Neptune. It didn't seem to quite agree with the theory. Here we have history repeating itself. Lowell said, there's another planet out there. They called it Planet X. And in 1930, one of Lowell's co-workers, Clyde Tombaugh, discovered Pluto. And it was about where the prediction said, but it was too small. And in fact, we now think it was just a human error, a coincidence. We don't even consider Pluto a planet. It's a dwarf planet. And it certainly would not be big enough to move Neptune at all. It's just like an escaped moon. It's not really a planet. So this is an example of when we trusted the theory too much. What was the real explanation? Well, they had done their math wrong. They had put in the wrong number for Neptune's mass. And once they corrected that, the orbit of Neptune was correctly predicted by Newton and by Kepler. So the discovery of Pluto was a coincidence and an example of human error. Kind of ironic. So this is a danger. If you have a theory and it's successful, and if you have some problems in your data, you might have an incorrect interpretation. You might be led to a false idea. This discovery was thought to be confirming the theory, but it wasn't. It was just wishful thinking. So this is a real but often unrecognized danger of over-reliance on any given scientific model. It's a weakness in the way we humans think. We may cling to our cherished model. When some data disagrees with it, we may say, no, I ignore that. And we may consider something to be a proof or a confirmation of our idea, and it really isn't. So the past success can set us up for failure. And there were other failures in this story. Mercury's orbit was not quite what was predicted. So what do you think they said? They said, there must be another planet closer to the sun. We can't see it because the sun is so bright. The orbit of Mercury was just a little bit off. So they even named this new planet. You're going to laugh. They called it Vulcan. Vulcan is not there. There is nothing there. And yet people were so sure that that must be the explanation. Other people, when we finally realized there is nothing inside the orbit of Mercury, we looked carefully, they thought maybe that R squared factor isn't right. Let's tweak the theory. That was one option. Change the theory a little bit. But actually what we see here is that universal law of gravitation, it fails. It fails for Mercury. And no Vulcan was ever discovered. Newtonian theory had to be abandoned. Again, it worked so well, but now we say, okay, it was only approximately right. It was replaced by general relativity. Albert Einstein, everyone has heard of Einstein. He said, things don't orbit because of gravity. They orbit because mass warps space, and then the planets go in the straightest line they know how, in this warped space-time. So space-time is curved, mass warps it, and then that tells the masses how to go. So they're trying to go straight, they end up orbiting around. It's a simple concept that requires quite a lot of calculation, and it gives the right answers where Newton was a little bit off. So, general relativity explains it all. Not. It explains more than before. See how this repeats itself. It explains the path of Mercury, slight precession of the orbit. It explains gravitational redshift, how light leaving a star changes its color. It explains light bending around a black hole or around a large star. This has been measured during an eclipse. We see the stars behind the sun are at a slightly different position, or they seem to be because the light bent. And you see that bottom image with the curved path of light. This is general relativity. Oh, and the last picture is we have multiple images. Right there in the center of the screen, we have 4 different images of the same star because the light bent and we see it coming from 4 different directions. We see the same star in 4 places. Space is curved. We're pretty sure of that now. Okay, but here's an irony. Newton's law, it was called a natural law of gravity, has been replaced by what we call now the theory of relativity. Isn't that funny? You think of a theory as not very reliable, but it's more reliable than that so-called law. The law was wrong. Wherever they give different answers, relativity is right, Newton was wrong. So, is this true finally? Is this the final answer to explain the motion of everything in the heavens? No. At the very small level, we need quantum physics. General relativity fails. In fact, quantum physics is also an approximation to the truth. We're learning more, but we're never getting the final answer. When you have very fast speeds, we have to use special relativity. When we have large masses, we must use general relativity. When we have small size, we must use quantum physics. And in fact, we have no explanation that works all the time. Science has brought us a long ways, but not to truth. So these generalizations are partly successful, and there are a number that people propose today to try to go beyond. And this is just, we're trying, we're doing our best, but we have no proof of any of these explanations. If it works, we're going to use it. That's the power of science. But if we do not get new insights of how the universe works, then it's probably the wrong track. Okay, so there's some take-home lessons to summarize. It's a fundamental truth about science and human nature. Science and human reason is not the answer to everything. It's inadequate. It's not the way to find truth. We can get closer and closer, but it's not proof, it's not truth. Science is tentative, it's limited, it cannot guarantee anything. We use observations and we use theory, and new experiments may reveal some errors in what we thought was truth for 1,000 years. History gives us no reason to believe that we have eliminated all the errors. And so we should realize that even today, we may say this works, but it may not be the final true answer. Our current explanation governs what kind of things we do, what experiments we try. So we may be limiting ourselves. And some useful experiments may not be attempted because of the way we think. So we need to be aware of these limitations. Deciding which data are reliable and which ones are maybe a mistake, that's a value judgment. So there are discrepancies between theory and observation, and we've seen the different human responses, and we've seen examples of how those happened. We would like each new theory to be more powerful, to be better, to be more accurate, and to work in a wider range. We would like it to help us understand how the universe really works. Einstein used to say that he wanted to understand the mind of God. So this, how God set up the universe, and real deep understanding of how things work. But we are never there. We're getting closer and closer and closer. I'll ask your forgiveness for using a term from pre-calculus. It's an asymptotic approach. So it's getting closer and closer and closer and closer. Little by little, we are approaching truth. But we're still wrong. Science is limited. There are no guarantees. Maybe there will be a never-ending sequence where we get closer and closer. Maybe throughout all eternity it will be this way. Now, we can eliminate wrong answers. This doesn't work. We got a problem here. Choose a new model. But we cannot say that what we're left with is true. There's no reliable way to decide if two theories give the same answer. So science is useful, and our theories are useful, but they don't have to be true. As a way of learning truth, science is not enough. It can be relied upon to help us figure out what's not true, but it cannot be relied upon to find the true nature of reality. So those who say science proves there's no God, I'm sorry, science doesn't. And it actually can't prove even the theories that we use. The materialistic worldview, matter is all there is, there's no spiritual, that has internal problems, which I think give us good reasons to not use it. The biblical worldview actually gives us more sensible explanations. Francis Schaeffer said, the biblical worldview taught that there is a reasonable God who created a reasonable universe. And so man, by the use of his reason, could find out the universe's form. So this makes sense. Why is the universe logical? God made it that way. Why can we understand? God made us with that power to understand. We can't understand all of what God shows us, but we can understand some truth. And that makes sense. So this tells me, why is the universe reasonable? Why does science even work? It tells me that I should use my brain. God gave me this intelligence to use and to try to figure out things. It also teaches me humility. We're not going to have the final answer. We should admit it. We should admit that we are limited. We should look at nature with awe and delight. It's amazing. It's the work of a master. And we should enjoy this, enjoy the wonders of the universe, and enjoy learning. What do you think we're going to be doing throughout all eternity? We'll be learning. The unfolding of deeper and deeper understanding, the appreciation of ever more expansive vistas. Kepler was struck by this divine harmony, and David said, "The heavens are telling the glory of God." The expanse, the firmament declares the work of his hands. And Ellen White says in The Great Controversy, pages 677 to 78, in the new earth, in the recreated heavens and earth, the acquirement of knowledge will not weary the mind or exhaust the energies. Still there will arise new heights to surmount, new wonders to admire, new truths to comprehend. Upon all things, from the least to the greatest, the Creator's name is written, and the years of eternity as they roll will bring richer and still more glorious revelations of God and of Christ. For us, as students of God's creation today, although we are admittedly seeing through an imperfect way, through a glass darkly, as it says in 1 Corinthians 13, our experience of heaven can begin now. Thank you for listening to this presentation. Let's have a prayer to close the Sabbath. Heavenly Father, we stand in awe. We are amazed at the amazing universe you've created. We thank you for it. We thank you for the wonders of the universe and the amazing patterns and incredible explanations that show how things work. We also praise you that you have made us capable of understanding even a little bit of your amazing creation. You could have made a race of robots that would just obey, but instead you made us with free will to choose. And we ask that you will help us to choose you every day so that not only can we go home to heaven when you return to bring us there, but in the meantime, we can honor you for your handiwork and for what you are doing in our lives. We thank you in Christ's name. Amen.